z1 equals a plus bi and z2 equals c plus di, where I squared equals minus 1. Show that the conjugate of z1 plus z2 equals the conjugate of z1 plus the conjugate of z2. The conjugate of z1 is got by changing the sign of the imaginary part. So the imaginary part of z1 is plus b, so we just change it to minus b. We do the same for z2. We change plus d to minus d. The real part stays exactly the same. Now let's add z1 onto z2. So to add two complex numbers, we add the real parts together. So we get a plus c, and then we add the imaginary parts together. So we get bi plus di, which can be written as b plus d times I. Now let's look at the conjugate of z1 plus z2. We just change the sign of the imaginary part. Well, the imaginary part is plus b plus d, so we change that to minus. Let's get the sum of z1 bar and z2 bar. So we add the real parts together, we get a plus c. Then we add the imaginary parts together, so we minus bi minus di. But we can factorize I out of this here, and we can take the minus sign out as well. So we can write that as minus b plus d times I. And you can see now that these are the same. That's what we had to show. We had to show that the conjugate of z1 plus z2 equals the conjugate of z1 plus the conjugate of z2. Now I just want to do something more. I want to look at the product of the conjugate of z1 with the conjugate of z2. So we want to take a minus bi and multiply it by c minus di. So what's the real part going to be? Well, the real part is got by multiplying a by c, which is ac. Well, that's one part of the real part. The other part of it is got by multiplying minus bi by minus di. That's going to give plus bdi squared. But I squared is minus 1, so bdi squared is minus bd. Now, let's get the imaginary part. If we multiply a by minus di, we get minus a di, and bi minus bi by c is minus bci, and we can factorize I out of this. We can write it as minus ad plus bc times I. Now let's look at the conjugate of z1 multiplied by z2. So we have to multiply z1, which is a plus bi, by z2, which is c plus di, and then take the conjugate. So we do the multiplication first. So we have a times c is ac. If we multiply bi by di, we get plus bdi squared, which is minus bd. Now for the I terms, we have ADI plus BCI. We can write that as plus AD plus BC times I. Now we want the conjugate of this complex number. Well, the real part is this here. These two terms constitute the real part. We don't want to touch that. What we do want to do is change the sign of the imaginary part. Now the imaginary part is AD plus BC, so we want to change its sign. We want to change this plus to a minus. So here is another interesting fact. We see that the conjugate of z1 times the conjugate of z2, which is this thing here, is actually equal to the conjugate of z1 times z2. So these are equal. Solve the quadratic equation 2i times z squared plus 6 plus 2i times z plus 3 minus 6i equals 0, where I squared is minus 1. Now, this is a quadratic equation. It's a quadratic equation in z. We have a z squared term, we have a z term, and we have a constant term. The coefficients happen to be complex numbers. A, which is the coefficient of z squared, is 2i. B, the coefficient of z, is 6 plus 2i. C, the constant term, that's the term that doesn't involve z, is 3 minus 6i. So we write down our quadratic equation formula and plug everything in. So we have minus b, so we have minus 6 minus 2i, plus or minus the square root of b squared. So we have to take 6 plus 2i and square it. 6 squared is 36. 6 times 2i is 12i. Double that, we get 24i. 2i all squared is 2i by 2i, which is 4i squared, which is 4 times minus 1, which is minus 4. Then we have minus 4 times a, which is 2i, times c, which is 3 minus 6i. And the whole lot is divided by 2 times a, where a is 2i. Simplifying what's inside here, we have 36 minus 4 is 32. Minus 4 by 2i is minus 8i. Minus 8i by 3 is minus 24i. Minus 8i by minus 6i is plus 48i squared, which is minus 48. Very conveniently, the I terms disappear. 32 minus 48 is minus 16. The square root of minus 16 is 4i, because we can write minus 16 as plus 16 times minus 1. So we have the square root of 16, which is 4, times the square root of minus 1, which is I. Of course, it could either be plus or minus I. So there are two possibilities here. We could have plus or minus 4i. But that's taken care of by the plus or minus in our formula. So if we take the plus sign here, what do we have? We have minus 6 minus 2i plus 4i. That's minus 6 plus 2i divided by 4i. That's one solution, although we have to get this as a single complex number. If we take the minus sign here, we have minus 6 minus 2i minus 4i, which is minus 6 minus 6i divided by 4i. So how do we write this thing here as a single complex number? Well, what we do is we multiply above and below by I. That will turn the denominator into a real number. I times I is I squared, which is minus 1. So in the denominator we get 4 times minus 1, or minus 4. In the numerator we get I times 2i is 2i squared, which is minus 2. And then we have I times minus 6. And we can break this down to minus 2 over minus 4, which is a half. Minus 6 over minus 4 is plus 3 over 2 times I. Now we do the same to this here. We multiply above and below by I. So this will become I times minus 6i is minus 6i squared, which is plus 6. And I times minus 6 is minus 6i. Underneath we get I times 4i is 4i squared, which is minus 4. So we have 6 over minus 4, which is minus 3 over 2. Minus 6 over minus 4 is plus 3 over 2. So here are the two solutions of the quadratic equation. We can plug our quadratic equation in here. It's 2iz squared plus 6 plus 2i times z plus 3 minus 6i equals 0. We don't need brackets around the 3 minus 6i, of course. So here it is, and here are the two solutions. Z equals cos of theta plus I sine of theta. Use de Moivre's theorem to show that z to the power of n plus 1 over z to the power of n equals 2 cos n theta for n an element of n. So n is a natural number. That means a positive integer. Here is z. To get z to the power of n, we use de Moivre's theorem. So we just put this to the power of n. So we get z to the power of n. The modulus of this number is 1, so we just have 1 to the power of n if you like, so we can forget about the modulus. We just multiply the power by the argument, so we get n times theta, so we end up getting z to the power of n equals cos n theta plus I sine n theta. To get 1 over z to the power of n, we realize that we can write it as z to the power minus n. So algebra of complex numbers follows the same rules as the algebra for real numbers. So we can do this, and we can apply de Moivre's theorem. De Moivre's theorem is true for negative integers as well as positive integers. So to get z to the power minus n, well, you could multiply minus n by your angle. So we get cos of minus n theta plus I sine of minus n theta. Now the cos of minus n theta is just the cos of n theta. We used result at the cos of minus a equals cos of a. Also the sine of minus n theta is minus sine n theta, using the result that the sine of minus a is minus sine a. So we can take this minus sign out here. And finally then, to get z to the power of n plus 1 over z to the power of n, well, we just add this onto this here. So we get cos n theta plus cos n theta, giving 2 cos n theta. Okay, this is actually the same as this. This is cos n theta. So we add the real parts. And then we add the imaginary parts. And we're going to get 0 when we do that. Expand z plus 1 over z to the power of 4 and hence express cos to the power of 4 theta in terms of cos 4 theta and cos 2 theta. So we're expanding a binomial here. We have two terms in this, so it's called a binomial. So we have 4c0 times one of these terms to the power of 4. I'll take z to the power of 4. And we multiply by 1 over z. That's the other term, to the power of 0. And the next term is 4c1 times z to the power of 3. So we decrease the power of z by 1. We increase the power of the other term by 1. The other term is 1 over z. Then we have 4c2 times z squared times 1 over z squared plus 4c3 times z to the power of 1 times 1 over z cubed plus 4c4 z to the power of 0 times 1 over z to the power of 4, and this is the last term. So you see that we're decreasing the power of z from z to the 4 down to z to the power of 0, and we're increasing the power of 1 over z from 1 over z to the power of 0 to 1 over z to the power of 4. Now we could use Pascal's triangle to calculate some of these coefficients, to calculate the 4c0, 4c1, 4c2 up to 4c4. We could look at the fourth row of Pascal's triangle. To get Pascal's triangle, we have ones down one side and ones down the other side. Then we have 1, 2, 1. These are the combinations used in squaring a binomial. You know, for squaring, say, a plus b, we would have 1a squared plus 2ab plus 1b squared. These are the coefficients when we cube a binomial. This is 3c0, 3c1, 3c2 and 3c3. We just get these values by adding 1 and 2 together gives 3. Adding these two together gives 3. We have a 1 here and a 1 here. 3 plus 1 is 4. 3 plus 3 is 6. 3 plus 1 is 4. So this is the row for expanding out the binomial a plus b to the power of 4. So 4c0 is 1. So we have 1 times z to the 4 times 1 over z to the power of 0. Well, that just gives us z to the power of 4. 4c1 is 4. So we have 4 times z cubed times 1 over z. So one of the z's cancel. So we get 4z squared. Then we have 4c2, which is 6. So we have 6 times z squared times 1 over z squared. That just gives us 6. The z squareds cancel out here. We have 4c3, which is 4. So we have 4 times z times 1 over z cubed. So that's going to be 4 over z squared. So we get 1 over z squared from this. 4c4 is 1. Z to the power of 0 is 1. So we just get 1 times 1 over z to the power of 4. Now we can write this expression as z to the power of 4 plus 1 over z to the power of 4. That's this here. We can factorize 4 out of this term and this term here. So we get 4 times z squared plus 1 over z squared, and then we have plus 6. Now the reason we do that is because we want to use this result here. So we want to apply this result when n equals 4 and also when n equals 2. So you see that this thing here is the same as z to the power of n plus 1 over z to the power of n when n is equal to 4. So we just plug 4 in for n here, so we get 2 times the cos of 4 theta. So that's what we have here. Now, what about z squared plus 1 over z squared? Well, that's the same as this thing here with n equal to 2. So we get 2 cos times 2 cos of 2 theta. So this here is 2 cos 2 theta. And we have to multiply it by 4, and then we add on 6. Now, we want to somehow bring cos to the power of 4 theta into this. We've looked at the right hand side, and we've used this thing to rewrite the right hand side in terms of cos 4 theta and cos 2 theta, in terms of these. What about this here? Well, we see that z plus 1 over z is the same as this thing with n equal to 1. When n equals 1, z plus 1 over z is going to equal 2 cos of 1 theta. 2 cos of 1 theta. And we have to raise it to the power of 4. Okay, so this is z to the n plus 1 over z to the power of n with n equals 1. So we plug 1 into the right hand side, so we get 2 cos of 1 theta or 2 cos theta, and when we raise it to the power of 4, we must get this here. So now you can see how we can write cos to the power of 4 theta in terms of cos 4 theta and cos 2 theta. So raising this to the power of 4, what do we get? We get 2 to the power of 4, which is 2 2 is 4, 2 4 is 8, 2 8, 16. Get 16 cos to the power of 4 theta equals this. So we have to divide all of this by 16. So we get 2 over 16 here, which is 1 8. 8 over 16 is a half. 6 over 16 simplifies down to 3 over 8. Let's just do a few checks of this thing. This is supposed to be true for all values of theta. In other words, it's supposed to be an identity. So, for example, if we plug in theta equals 0, it should work out. Well, if we plug 0 into the left-hand side, we have the cos of 0 to the power of 4. That means we get the cos of 0, which is 1, and raise 1 to the power of 4, so we get 1. If we plug 0 into the right-hand side, we get 1 8 of cos of 0, which is 1 8, plus a half times the cos of 0, that's a half, plus 3 eighths. Well, 1 8 plus a half plus 3 eighths is actually equal to 1. So it does check out when theta is equal to 0. Just as an exercise, I'm going to stick in another value for theta. This time I'm going to let theta equal pi over 2 radians, which is 90 degrees. So cos to the power of 4 of pi over 2 just means we must get the cos of pi over 2, or the cos of 90 degrees, which is actually 0. 0 to the power of 4 is 0. Now let's look at the right hand side. We have 1 8 times the cos of 4 times pi over 2, or 4 times 90 degrees. That's 360 degrees, or 2 pi radians. Plugging pi over 2 in here, we get a half cos of 2 times pi over 2 radians, or pi radians, and then we have 3 eighths. So if we work out all of this, we should get 0. Well, the cos of 2 pi radians is the same as the cos of 0 radians, or 0 degrees, which is 1. So we get 1 8 times 1. The cos of pi, or the cos of 180 degrees, is actually minus 1. So we have a half times minus 1, which is minus a half. Then plus 3 eighths. 1 8 plus 3 eighths is 4 eighths. 4 eighths is a half minus a half is 0. So when theta equals pi over 2, it also checks out. So it checks out for these two values. We can't be absolutely sure, of course, but it's very likely that if it works for two of them, it works for all of them, all values of theta. And that is indeed the case for this identity.